let's put the intermediate value theorem to work. One of the things that we're interested in is finding the roots of polynomials. A lot of other problems in real world stuff, or even just abstract math problems that we solve for their own good, can be phrased in terms of solving polynomial in the variable x is equal to 0. So we'd like to know, how can we find these roots even when we don't have things like the quadratic formula? There is no quadratic formula for fifth degree polynomials. So what we can do, and this is exactly the way that computers would work on this kind of problem. We just programmed this idea in for websites like Desmos.com. The idea is that this function is continuous, and I know it's continuous because it's a polynomial. So if I want to zoom in on a root, all I need to do is to find one place where the function is negative, find another place where the function is positive, and in between those, somewhere, because of the intermediate value theorem, the function must be exactly equal to 0. So in my setup for the intermediate value theorem, I'll say a equals maybe -1, b equals, let's say, minus a half. I get -1 for the value f of a. I get, oh, it looks like positive 0.8 something for the value at minus a half. 0 is between those two y coordinates, so this function must pass through y equals 0 somewhere in between. So that says I can zoom in a little bit more. I'll have my x starting at -1, my x going up to minus 0.5. Okay, so on this scale, I can see where that root is. Again, I can use the intermediate value theorem to justify zooming in a little bit more. At minus 0.9, the function is negative. At minus 0.8, the function is positive. So I can reason out that somewhere in between, the function must be exactly equal to 0. So I'll zoom in a little bit more. Let's go from minus 0.9 to minus 0.8. Okay, at this scale, I can see that the function is negative at minus 0.87, and it is positive at minus 0.85. Actually, it's minus at 0.86 as well. It's just very, very close. Let's zoom in further. So on the left, it'll be minus 0.86. On the right, minus 0.85. Now, the graph has flattened out quite a bit, so I need to zoom in on the y-axis as well. Let's go from y is minus 0.1, 0.1 to positive 0.1. That's a little bit easier to look at. And every single time, I'm just looking for one place where the function is negative, one place where the function is positive. It has to cross y equals 0 in between. So now I've got 2 decimal places correct. This number is between minus 0.86 and minus 0.85. So the first 2 decimal places is this number is minus 0.85 and change. Desmos is saying that that should be minus 0.8567. Now that's not the exact value. And I know that's not the exact value because I'm going to zoom in even more. So I'm going to, so I want x from minus 0.8656 to minus 0.8658. Again, I need to zoom in on my y-axis. A little bit more than that. No, that should be good. And I just need to find one place where it's negative. It's negative all along this range. Then it crosses. And lo and behold, minus 0.8567 is where Desmos said this function is equal to 0. But if I zoom in even more, I can see that that's not quite true. I can see that there's actually a gap here. I don't know. Stop doing that. I don't know if you can tell that on your monitor here, but here's that x coordinate that Desmos was telling me is the root of the function, and it's not. This is. Oh, hang on, that looks funny, doesn't it? Desmos is rounding off to the 4th decimal place. And Desmos can see and show me where that root is in between, but it can't tell me with any more accuracy, at least not in the decimal expansion here. Now, everything a computer does is something that a human programmer told the computer to do. What did we tell this computer to do? We told it to look for negative values on the left, to look for positive values on the right, and somewhere in between has to be the root that I'm looking for.